Now, not all of our scientific reasoning is inductive, and in fact, most scientific reasoning is abductive and involves what is called the inference to the best explanation. So I want to use this opportunity to raise another concern that has shown up in the philosophy of science, besides the concern of the problem of induction. And that is this. It's a fancy term, but the idea is called the underdetermination of theory by data. Pretty fancy sounding, right? But you can actually prove that taking any set of observations that you want, take any set as complicated, as big as you want, there's always provably going to be more than one theory that explains those observations. Now, I'm not going to spend too much time in this course talking about the theory of explanation. We're going to say a few things, but right now just work with an intuitive understanding of what I mean by explains those observations. It offers a coherent story about why it is that we observed what we observed, and it offers predictions about what we can expect to observe next. An explanation is going to posit a bunch of different kind of entities, physical entities with a scientific explanation, particles, molecules, atoms, different classes of species. You get the idea. It depends on the science that we're doing. But here's this whole set of observations. Here's an explanation of it. The explanation is going to offer us some ontological entities that do the explaining. It's going to give us a story about why we've observed what we've observed, and it's going to then make some predictions about what it is going forward. For any set of observations, there's always going to be at least two, if not more, explanations of them. And I'm not going to get into the way to prove that. Take that for a moment as just a given. Well, now this is a problem for scientists, because if science is all about making observations and then offering explanations of them, and there's never a unique explanation for any set of observations, then how do we decide which explanation is the best explanation? This is where scientists offer a bunch of criteria for determining what counts as the best explanation. And there are some concerns at times with what scientists have chosen to be on that list of criteria. One is following a principle of Occam's razor. Here the idea is that if I have a set of competing explanations of observations, I ought always choose the one that posits the most, that's the simplest. And that can often involve positing the fewest number of different kinds of things to do the explaining. Now, some people think that that's really an important principle to guide our scientific thinking, and others don't agree with that. But it is one that has a long tradition in our thinking. If I have two competing theories to explain these observations, and one can do all of the explaining and all of the predicting by just saying, here are 10 entities that do all the work, and another one says, here's 250 that do the same work, then I ought to choose the one that has only 10. It's simpler, and on that respect, it's the better explanation. Another standard is how much predictive power does a theory have? It's one thing to explain everything that we've so far observed. It's another to offer us a theory that can help us predict what we will observe next. In the never-ending battle in the public arena about scientific theories and their worth, I find that many people really don't understand what a scientific theory is. I'm not going to go into this in much detail. I recommend the show Cosmos if you really want to see this spelled out in great detail and profoundly. I will say, however, that it's not merely enough for just anyone to cook up an explanation of why we're seeing what we're seeing from the past. We also want a theory to be able to tell us what to expect to see in the future. And then when we do find those things, that confirmation will help us to build a better theory. It will support a theory, or if things are different, it will help us reject a theory and move on to something different. Now, we don't have the space in this course to get into the nitty-gritty of confirmation theory in the philosophy of science, and there are some issues with that. But it is important to emphasize that what makes the theories the best theories in part has to do with their predictive capabilities. This is one of the hallmarks of science, is not only that it can explain the past, but also it can tell us what to expect in the future through an analysis of the data, through a set of observations and so forth, and an application of abductive reasoning, inference to the best explanation. Something that scientific theories may seem to be giving us that we really are interested in their explanations are causal explanations of things. And this is a topic I want to wrap up this module by discussing. So it's not just that scientific theories give us any explanation, we think at times that they give us a causal explanation of things. It's not enough. I mean, one of the lessons that you learn when you take a statistics class is, here's one thing that happened and here's something else that happened, and look, they always happen together. Well, correlation does not mean causation. We have a variety of different methods at our disposal to try to show that there's a causal relationship between two things and to distinguish that from a correlation. We know, for instance, that whenever Clark Kent is absent, Superman is out saving the day. That's a correlation. It's also, in some sense, causal, because Clark Kent is Superman. Clark Kent's being absent is in part causally responsible for Superman being out there doing what he's doing. But it might be the case that Jimmy Olsen, just by happenstance, also is always absent when Superman is out and about or when Clark Kent is absent. And that's not a causal connection, that's a correlation. I think you get the rough idea between two things happening at the same time but not having really much deep connection, and those things that have a causal connection. Now, some scientific theories, or some philosophers of science, think that at the end of the day, scientific theories don't give us causation, that causation as a concept is something that falls out of the most advanced scientific theories, that scientists should avoid talk of causation. And here they're following Hume, who's a little bit skeptical of there being a deep notion of causation. All the same, in our ordinary experiences, we talk about things causing other things all the time. And we do look for explanations, scientific or otherwise, to explain this relationship. But what is causation? Well, philosophers have spent, per usual, a tremendous amount of time thinking about this, and those who aren't skeptics have given a variety of different answers. One of the more popular ones is often referred to as a counterfactual analysis of causation. Here the idea is that we can say that one event causes another event just in case were the former event not to happen, then the latter event wouldn't happen either. That is the counterfactual dependency. Consider the following example. Dr. Doom, Victor Von Doom, has invented some kind of combination of science and sorcery death ray glove. And he's about to use it on the members of the Fantastic Four. And he fires at it. And Sue Storm, Invisible Woman, just at that time, throws up a force field. The ray deflects off the force field, hits Dr. Doom, and knocks him unconscious. It doesn't kill him, but it knocks him unconscious, right? Now here we would say that Sue Storm's force field caused Dr. Doom to be knocked out. Were she not to have put it up, he wouldn't have been knocked out. That's the counterfactual analysis. The reason, the explanation for why Sue Storm's force field caused Dr. Doom to be knocked out is because the counterfactual is true. Were she not to have done that, he wouldn't have been knocked out. That's the rough story about what is the essence of the causal relation. The causal relation is captured by the truths of these counterfactuals. Now, it sounds so nice and simple, right? You're probably waiting for me to say, but it can't be that simple. And that's because it can't be that simple. There's been a tremendous amount of concern with this counterfactual analysis, and I'll just give you one of the many problems that have been leveled against it. Consider now a second scenario. We have Dr. Doom with his death ray gauntlet about to fire it on Sue Storm, and let's say Reed Richards is right next to her, so about to fire it on them. And unbeknownst to Dr. Doom, Ben Grimm, the Thing, is right around the corner, right? And so Dr. Doom fires his death ray, and Sue Storm's shield is released, and the death ray bounces off of the shield and knocks Dr. Doom out. But also in this scenario, there comes Ben Grimm, ready, unbeknownst to Dr. Doom, to punch Dr. Doom in the face. I mean, he's almost there, and it's just a split second earlier that the shield goes up and the death ray bounces back on Dr. Doom. Now, is the counterfactual true, right? That were it not the case that Sue Storm's shield went up, it would not be the case that Dr. Doom was knocked unconscious. No, in this scenario, that counterfactual is not true. If Sue Storm didn't put up her shield, Dr. Doom would still have been knocked unconscious by a different cause this time, by Ben Grimm. So does that mean that her force field doesn't cause Dr. Doom to be knocked unconscious just because there's this other agent here who would replicate the effects? Well, on the basic counterfactual analysis, unfortunately the answer is yes. That means that there's not a causal relationship, but that seems really unintuitive. And this is just one of some examples that have been raised against the counterfactual view. Problem is, the counterfactual view is probably one of the best ones around. And so, as you can imagine, philosophers have spent many decades, many centuries really, but in particular in the past several decades, thinking about how best to save the counterfactual view of causation.